Today we're starting the first of a three-part series, unboxing Hyperledger Fabric 1.0. So the announced general availability of 1.0 is June of this year. So the alpha has been released and they're fixing bugs and stabilizing things. And we had originally thought of having a hands-on sort of session to bring people to Hello World with Fabric on a one-day event. But then we realized there's a lot of content to cover, so we had a preliminary event a few weeks ago, and we thought it's better to break it up into pieces so that it takes time to digest all of the different aspects. And so we're going to cover the content actually in 2 sessions on evenings, and then on the day, May 20th, again, we're going to have more content, and then we'll get into the hands-on session on that day. So if you're interested in being confident of setting up your own Fabric network and you haven't done that yet, and you'd like to do it in a group setting with us, please join us for that. So the first session is about consensus and ordering. And the key innovation in 1.0 is the scalability of that process. So one of the problems with business use of distributed ledgers was the number of transactions they can process per second. And Fabric essentially solves that and makes it arbitrarily scalable effectively. And so how that mechanism works, what are the different consensus options available, and so on, will be something that Zaki will explain to you today. Zaki has been studying consensus for 3 years now.
4 years.
4 years now.
I have a weird hobby.
Yeah, this is hobby. He does, whenever he has nothing else to do, he looks at the latest consensus algorithm. So if you have some weird question that you want answered about consensus, please ask it today, and if he's not able to answer, coffee is on me. The next session is going to be about the business confidentiality that's needed. So that's the other aspect of distributed ledgers that's been a challenge. Fabric 1.0 has the concept of channels and various different levels of access to information in a channel. I'll describe some of those features in the next session, and then on the Saturday when we have the hands-on event, we'll spend about an hour and a half talking about more the nitty-gritty, like SDKs and the membership services and the things that make it permissioned and all of those things that you actually need to deal with when you want to set up a network. So that's kind of the plan, and so with that, I'll turn it over to Zaki for the session.
Hello. So this is going to be, so depending on how many questions and what order we want to go in, but I like being bombarded by questions, so feel free to interrupt me. Can we do a round of introductions, and can people also tell me, like, how much of a background do you have in this stuff? Do you know what Fabric is? Do you even know what I'm talking about when you talk about the Fabric order? Have you just encountered blockchains for the first time? Could we start with you?
My name is Subramanian. I'm interested in blockchain and have sort of some idea of what the background is.
Okay.
Hi, I'm Melanie. I work for Ernst & Young as a consultant in blockchain. Blockchain is my full-time job, but I can always, I don't know, I feel like I can always learn a bit more about blockchain, so I have high hopes for tonight.
Mohammed, I work for Visa, and I have a decent experience with Fabric.
Cool.
My name's David Chen. I'm currently working a smart contract-based application, and I've tried Fabric, Ethereum, and other stuff.
Natalie, I run a small startup. We work a lot with Ethereum, and I think I spent 2 or 3 days at a hackathon working on Fabric. So.
My name's Andy. I'm a freelance developer. I've got Ethereum projects. I don't know anything about Hyperledger, so this is all new to me.
Hi everyone, my name is Abhishek. I work for Accenture Ventures, and I'm here at blockchain efforts. I know about Hyperledger at a very high level.
Hi, my name is Philip Sanga. I know something about blockchains, but fairly preliminary stuff. So I'm just
Ashish, I just started playing with Hyperledger a couple of weeks ago, so looking forward to learning more.
Mark acknowledge, work for Oracle, building out some blockchain service capabilities, and some theoretical familiarity with Fabric, but not enough hands-on.
Maurice, I work at Oracle. I work with Hyperledger 2.6 and 1.0. Quite a bit.
Well, I'm a Sikram America, I'm developing interface for Japanese clients.
My name is Sanjay Saxena. I work for IBM as a developer application for blockchain. I recently got started with this technology, so
I'm Mukesh. I work with Cisco. I'm also working on blockchain project. And we work closely with blockchain and some projects.
I'm Joshua. I'm a student at SAP. I'm currently working on the topic during my internship. I have to look at several blockchain technologies.
I'm Carla. I work for Quest Software in program operations. I'm very novice to blockchain, but very interested in the capabilities of the blockchain IP and how it applies in business applications.
I'm Joshua, and I work with Carla at Quest Software. I don't know anything about the Fabric orderer. I did read a little bit about the composer today with the Hyperledger announcement.
Yep.
I'm interested in that, sort of how things come together. But not new to blockchain, but interested in the commercialization aspects of how you build applications and drive cloud adoption.
Yeah, my name is Yadini. I'm from SAP Ariba. I'm using the Fabric application in the supply chain.
Cool.
My name is Brian Gardner. I'm a chip and IoT guy. I've been studying blockchain for 3 or 4 years. I'm more familiar with Ethereum. I have a basic background.
I work for Oracle. Started working on Hyperledger.
Sanjay, I work at Oracle too, and ERP Cloud, and started looking at Hyperledger for last month or so. Really understand what I'm doing.
My name is Peter. I'm looking for work, so I'm kind of trying to learn everything I can from different technologies.
I'm Pluggable. I work for Oracle. Been exploring blockchain technology for about a year and a half, and experimented with Hyperledger 2.6.
SKU chain folks, other than Runga.
I'm Jordan. I work at SKUchain. I help Zaki build applications on top of Hyperledger.
Steven Particular,
now working for market development
Ravi, I'm from Oracle. Playing with Ethereum framework. Just getting
So Oracle people, are you coming all the way from like Redwood City?
Yeah. It's like not Oracle and the rest of everybody else.
I'm just curious, like, seems like an epic journey. Okay, so there are a couple people in the audience that probably know as much as I do, so hopefully they will aggressively disagree with me, which is what I'm hoping with. Nobody, I would say, globally our state of understanding of this stuff and how to communicate about it is in its infancy. Hopefully meetups like this is like a sort of helpful environment for figuring this stuff out. So. The podium is good? Okay, I will roughly stay here, or I'll try. So the idealized orderer is blind and fair. Start out with this idea that what we are looking for in an orderer is an orderer that will simply take in transactions, apply fair, rigorous processes to sequencing those transactions, and create a total order for the blockchain. In my mind, basically a blockchain is any system that has these two properties. You have a programmable distributed system, and you have a total order. A total order basically means that there is only one sequence one canonical sequence of events that all of the peers in the distributed system have observed. If you have these two things, you have a blockchain, and without an orderer, you don't have a blockchain. In the philosophy and the thought process of blockchain, what is the fundamental breakthrough that enabled Bitcoin was that you could have ordering by anonymous sort of peers using proof of work to determine what the total order was. That's the sort of computer science-y view of what is the Satoshi Nakamoto consensus breakthrough is anonymous ordering. What we are talking about in Fabric is pretty much the opposite of that, which is known ordering, but we are still building a system in which you have a total order. So we are going to talk a lot today about the idea of Byzantine fault tolerance. Byzantine fault tolerance was introduced by Leslie Lamport as a property of a distributed system. This is sort of the classical diagram from Leslie Lamport's original paper. You have the commander is trying to figure out whether or not is trying to get his armies to attack. He says to his lieutenants, attack, attack. Lieutenant 2 says to Lieutenant 1, he said retreat. If the commander is malicious, he sends different messages to Lieutenant 1, Lieutenant 2. A Byzantine fault tolerant system is a system in which, as long as you are above whatever your safety threshold is, which is sort of the classical Bitcoin 51% of hash power, every consensus algorithm will have a different safety threshold, the system will still do the correct thing. So the system will still be able to figure out that everybody said attack. Otherwise, or if you have exceeded or if you have more malicious actors in your system than your safety threshold, then the system will fail. Byzantine fault tolerance is what allows cryptocurrencies to function. Cryptocurrencies can function because they use a Byzantine fault tolerant consensus mechanism. With enterprise blockchains, what we are going to see and be discussing is a more complex set of trade-offs between fault tolerance and Byzantine fault tolerance, where Byzantine fault tolerance invariably comes at some cost in terms of throughput relative to a fault tolerant system that is not resilient to malicious actors in the system. So what Fabric has done in the blockchain space is they have created a continuum at various levels of the system between Byzantine fault tolerance and ordinary fault tolerance. And that's going to come up a lot. I want to spend a lot of time on this slide and do Q&A because if we don't understand the Fabric transaction lifecycle, we can't really have a meaningful conversation about what it is that we're here for. So the Fabric transaction lifecycle starts at the top and goes to the bottom. So some entity, some business application, the thing that's providing your user interface, the server behind your web browser, etc., proposes a transaction. The ledger simulates the transaction's execution. It executes it on an instance of the Chaincode, which is some Docker container containing your application logic. If there's an error, it gets reported back to the client. If you have used 0.6, you can see that that doesn't work very well right now, but it works better in 1.0. If there's no error message, then you go through this cycle where you go back to the Chaincode, you wait for success, you go back to the, if there's an error, you would go back all the way to the client. So this is like SDK, peer. The shim is just basically a standardized API between Fabric and Chaincode. And then finally you come back and you get endorsement if you have an endorsed Chaincode. So let's talk about this in a more specific context. Let's say that the Chaincode contained a set of bank balances. So your proposal is send money from Alice to Bob. So your proposal says, okay, I'm going to send money from Alice to Bob on this Chaincode running on this channel that has, money for Alice and money for Bob. At this point in the cycle, it's basically asking the question, does that Chaincode even exist? Then it's saying, can I change, can Alice send money to Bob? If, let's say, Alice doesn't have enough balance, then you get an error. If that error doesn't happen and you had success, then the Chaincode essentially will be so you have Chaincode and endorser Chaincode. The endorser Chaincode which this diagram captures poorly, the endorser Chaincode and the Chaincode will be running the same transactions. But the endorsers will be like, I saw that this was a correct transaction, that it was doing a valid thing, and I saw it in this sequence of things. I'm going to vote and send it to the orderer to then be put in the total order. So when does the thing actually happen in this context is only after endorsement happens, and then the endorsement goes to the orderer, and the orderer puts the transaction in a block. So the life cycle of a transaction in Fabric is extremely complicated, but what this basically allows you to do is it allows many different peers to interact with many different Chaincodes and share a single order. So you can have multiple compute channels that are doing different business processes, like verifying purchase orders, making payments, doing all of these things. All of this stuff happens essentially in parallel, all the way out into this final step, which when you have endorsement, and then the orderer has to operate synchronously. In a system like Ethereum, you don't have this life cycle. So what happens is that the sort of initial sending of the transaction is both validated for correctness and ordered at the same time. So the ordering, the miners are essentially, or the miners or the consensus engine, or depending on which version of Ethereum you're running, will actually do all of this stuff in one phase. Whereas this like multi-phase process, in theory, gets you parallelism in terms of validation and execution. But what it does is it sort of surfaces this complex architecture where you have orders, where you have clients, the peer, the Chaincode, and the order. That's it. I'm sure that was confusing, but I would like some questions. Like, what was the most confusing piece, Mohammed?
Is this is that flow, the flow in 1.2 or in 0.2?
It's the 1.0 flow.
Because I remember from the last time it sounded like this orchestration is happening by the client, not by the fabric. That the client gets what's called, I think, the anchor, and then passes it to other endorsers to endorse.
Yeah.
From this picture, it looks like the client is just making one call with the proposal, and that actually ends up getting endorsed in one call.
Yes.
Is that?
So the client makes one call, which once the client has deposited a proposed transaction into the system, the lifecycle is now independent of that client. Once the client has deposited the transaction into the system, and the system has evaluated the transaction to be valid, has a proper certificate, etc., like that client is registered with the certificate authority, etc., then that proposal will essentially make its way through to either to a chain code, and that chain code will then evaluate that transaction. But the evaluation of that transaction means that, as a practical matter, you evaluate that transaction, and then you have proposed an update to the state of the ledger, but it's only once you have endorsement and then ordering that statement is finally committed.
But the peer initiates the endorsement itself, or it just returns the proposal success to the client, and then the client initiates the endorsement?
The peer initiates the endorsement. In general, so you can imagine like a given chain code, let's say you have business A, business B, they've created a chain code for handling some business process. That chain code may only exist on those two peers. So they have clients that feed it to them. There are only two endorsers, and those two endorsers have peers that, those two endorsers are running the chain code, but they're also the endorsers. So when they both successfully execute the transaction, they're both free to then endorse and send the order.
So perhaps you can also elaborate on what defines a channel and how that contrasts with some of the other ways.
Yes, that is a super good question. Okay, so channels. Channels are, so you have a network. In that network, you have peers. So let's say you have a network. That network has a single order service. I wonder if I have a diagram for this. That's okay. Maybe. So this is a peer in the previous diagram. So this is order services nodes, and this is the actual ordering process. So also channels are next talk. So I'm not going to go too far into it. I don't want to steal Runga's thunder for the next talk. But the difference with what a channel is so there are, in a given network, to simplify a little bit, there is an orderer, there is an orderer, there's a blockchain essentially. That blockchain will then consist of transactions on sort of an open channel that is shared by everybody. That's the system chain code. And then you will also have specific channels that are between sets of peers, which contain data that's private to those peers. But those transactions that go into those channels, they're not validated by everybody. They're only validated by the endorsers on that channel. Does that make sense?
Yeah.
So let's compare and contrast.
Right.
So between a bunch of different blockchains. So if you send out a transaction to the Bitcoin network, you're essentially doing something similar to sending out a transaction to the open or the system chain code in Fabric. All of the peers on the network will validate your transactions. There will endorsement on the system chain code level will and is effectively a subset of those peers who are saying this is a valid transaction and update it, but everybody executes that transaction. If you send out a transaction to an Ethereum smart contract, same thing's true. The entire network executes the transaction. Everybody in Ethereum everybody who's in let's say the Ethereum public network is executing everybody's transactions regardless of whether or not they care about them. In the channel architecture, lets you set up a computing environment where you can execute shared code. But the only people who see that shared code and the only people who interact with that shared code are the parties to that channel. So you might get essentially a block that says, here is a commitment or here's a hash to a transaction, here's a transaction ID. But because you're not part of that channel, you don't execute any code. Does that make sense?
Right. Okay, I'll ask you questions later.
Okay. This stuff is really challenging to communicate about.
The question is, suppose I don't want to share the code until certain other checks are done.
Okay.
Then what is the way?
You don't want to share the code.
I mean, in this case,
you could have, in theory, actually, I mean, there's like on the roadmap support for this, which is you would share the ledger state without sharing necessarily all of the transaction execution architecture. But as far as I can tell, like, I also am somewhat troubled by exactly how you would pull that off. So it's a little bit of an open problem in my mind.
But I thought the endorser would need to do simulation, right? So somehow code has to be shared to a certain degree, right?
What was the question?
So you mentioned that in the future that you don't need to just share the ledger state, right? But in order to verify endorser, I don't know which one it is.
Yes, the endorsers need the code.
Right, you need to execute it. That
Yeah.
means to a certain degree you have to share.
Yes, absolutely. The endorsers on any channel must have the chain code. Okay. Sure.
Actually, 1.5 questions, just to make sure that I understood what you said earlier on about the channel. So although within a channel they're executing separate code from something without the channel, the code that is executed and what is written to the nodes is shared by all. Is that right?
No,
No.
it's the opposite.
Ah.
The code, if you are part of a channel, you are the only the people in the channel execute the code for that channel.
Right.
The ledger state updates,
Right.
which are going to be encrypted if you are not part of that channel, and the total order of the system, like which transactions happened in which order, essentially the blockchain is shared by the network.
So I think you agree, but so the state of the ledger is consistent throughout.
Yes.
Okay, so that's fine. So all right, that's fine. So that's fine. So just to my question, please.
But it may be opaque to you.
It may be opaque, but the nodes are consistent across
Yeah.
the network. That's fine. That's great. So just to an extremely newbie question here. Fabric chaincode and ghost chaincode. So Fabric is a ledger. Is that right?
Fabric is the pure binary. So it's the Fabric is like, how do I find peer, like the Fabric is how do I find peers on the network? How do I communicate? What are all the rules? What is all the code of essentially a node on the network? So Fabric is your proxy to the outside world. Everything to the right, so this is another thing out in the world, and this is your proxy between these layers and the rest of the world.
And can you just quick couple words on those different layers?
Okay. SDK.
Sure. Well, that.
Well,
Sure.
it has some subtleties to it.
Okay.
Because an SDK, the SDK communicates with the rest of the network basically with a peer-to-peer protocol. So the SDK gets a cryptographic identity just like it was another peer on the network. And it uses that cryptographic identity to transact. But unlike another peer on the network where it maintains the ledger state, the SDK doesn't maintain the ledger state. It just tosses transactions into the network and can query the network, other peers for information about the ledger state. but he can only ask a peer about stuff that it knows about. So to a certain extent, there is a mapping between like the idea of a light client in another network and an SDK, but it's not really a one-to-one notion. The fabric is the full peer. Is a full peer on the network. That is the peer binary. The shim is the API that exists between Fabric and Chaincode. Chaincode is your business logic. Endorser Chaincode is essentially the rule. So it's two things. Let's try and make this subtlety make sense. I am not an endorser on a channel. I see a transaction either sent to me directly or it comes in because, like it's been ordered. What do I do with that transaction? I go in and I execute it. I execute it inside my Chaincode. It updates my ledger state. So I get a transaction, I update my ledger state. If I'm an endorser, what I do is I execute that transaction, and then I endorse the execution of that transaction. So I actually endorse the ledger state update. And the rules according to which that endorsement then functions. Do I need one peer to endorse, or do I need these three peers to endorse? Essentially are handled by the endorser Chaincode. And then that basically the sign off on the endorser Chaincode level and the sort of proof that the endorser Chaincode ran properly for that channel is what can be used to tell the orderer, now you can order this transaction. Does that make sense?
It does. So it also implies that endorser Chaincode is programmable. It's not.
Yeah. So you have, every channel will have policy. That policy is given to is part of this, is the setup process for that channel. And I'm 100% sure that will be in the channel talk.
Thank you.
Okay. So this is a slide about the bad things that an orderer can do. So one of the things that we have to be really conscious of in these systems is what are the bad things. It should actually be what are the bad things an orderer can do. So an orderer can essentially double spend. An orderer can create two blockchains for which there's no obvious way to verify which one is the canonical blockchain. So you have a malicious order, or you have a malicious ordering process. The ordering process can then create multiple chains. A long-range attack is basically, this is your database state and it's been consistent for 3 months. Here's an alternative database state that is like missing a certain transaction. The orderer creates another one essentially for free and then shows it to the peers. The peers, you could have rules in a peer that basically say if somebody gives you newer state that is different from your older state, from your current state, and rewrites a certain amount of history, we're just not going to accept it. But that's actually it's a very subtle thing it's a very subtle nuance in the design of these systems about how resistant you can be. So we kind of trust the orderer not to do either of these things. If you have an order-dependent outcome, like any sort of auction, price matching, etc., that you are doing in your blockchain environment, the orderer can change the outcome. It can say, I want to do, if I put this transaction that has the right endorsements into the chain first versus this one, I can change the outcome of who wins the auction. And the final thing, which is kind of a subset of the previous one, is an orderer can just censor a user. An orderer can say, I don't like any, SAP transactions, I like Oracle transactions. I'm going to let more Oracle transactions into the network than SAP transactions. because I like it that way. Yes.
I'm not sure I understood the first point.
Yep.
So, for instance, if you take the Bitcoin, right?
Yep.
You would have like a fork, and then you would choose to either follow A or B of the fork,
Yep.
right? But in this one, what I'm understanding is that someone could like create a totally new product
Yep.
and submit it to the network, and
Yep.
the network could theoretically choose to go with this completely new.
Yes.
Okay.
So one of the things that the proof of work diehards like about proof of work based anonymous ordering is that the expenditure of energy means that there is a finite cost to create a second valid chain. In any of these permissioned networks that don't use proof of work, the cost of creating another indistinguishable chain, at least cryptographically indistinguishable chain, is 0. So as a result, these are the things we have to be aware of. We get these systems, they get much higher throughput than any proof of work system. They don't require us to build giant energy belching factories of hashing machines. But what we get is we get this property. And so as we go through this talk, we will see how we mitigate these things. But these are the concerns. So privacy is actually a mitigation against this. If you are transacting and computing in a channel that the orderer doesn't have access to, and that you have enough trust in your counterparties that they won't conspire with the orderer, or that you trust the orderer not to conspire with anyone in the channels, then the encryption of the transactions inside of your channel means that the orderer's ability to change outcomes is managed and mitigated. And that can work for many applications. And we talk more about that. How did this do? Did this make sense? So like, the basic idea is the orderer is now seeing a bunch of encrypted blobs of data. It's like, oh, this has enough endorsements on it. I can put this into the blockchain. But because the orderer can't see into what's in it, it doesn't know who sent the transaction. It doesn't know what the transaction was in regards to. It doesn't know that if I drop this transaction and include the next one, what will be the effect. So privacy is a technology, and it's probably the primary defense in the Fabric architecture from a malicious orderer.
Just a question though. So they still go through the orderer and they're ordered by the orderer, right?
Yes.
So why is it everything that goes through the orderer private?
So we will talk about that. I think I have a slide on it. But if we don't, talk about it. Okay.
Another question.
Yes.
Would an orderer be able to tell what channel things are coming in and let's say censor an entire channel?
That's a good question. I do not know the answer.
Sorry, what was that question?
Does the orderer know which channel incoming transactions are from?
So the question was, I'm going to do it for the internet people. The question was, does the orderer know what channel transactions are coming in from? And I do not know the answer to that question.
I just want a coffee.
Doesn't the orderer have to know because it communicates the transaction to all the nodes that are within this channel, or does it just
no? Because the order is shared across the network.
So it broadcasts all blocks to everybody on the network, regardless of which channel they are.
Yeah.
So there's nothing in the protocol that identifies the sender of that transaction with a channel attribute attached?
This is a good question. I don't know the answer to it. I hadn't thought of looking into it until you cleverly asked this question. It's actually a really good question. I don't know the answer. I know that so in the orderer API, it doesn't need to ever check this information. It doesn't actually deserialize the transaction and check what channel it's in. But it seems possible that it could censor an entire channel. So what are the situations where you might not need a Byzantine fault tolerant order? When most of the computation is in one of these private channels. When your order is highly secure and reliable. And what do you get from this? You get high transaction throughput from a centralized order. The less work, the less computation, the less cryptography that an order has to do in order to produce an order, there's an inherent trade-off between throughput and Byzantine fault tolerance. Yes?
So is the order publicly available? Is that public infrastructure? Is that order transactions between different sort of private Hyperledger instances?
So, one of the things we expect to see as Fabric becomes a deployable thing out in the world is, so these criteria, well, especially the middle one, the middle criteria is, so for the internet people, the question was, is the order like a public resource? So what a lot of people suspect, like one of the business models, I have a slide on this sort of later, one of the business models that's sort of embedded in like the kinds of infrastructure that a company like Accenture could provide for customers who are running is an order that is highly secure that you have to pay to set up channels on, and potentially pay for the throughput those channels consume. But you would be able to get, you would be able to share that order across many different business applications. And one of the things that's nice is the computation that is required, going back to the old architecture slide, is the compute of validating, executing that transaction could be arbitrarily complex, but it doesn't block anyone else on that order. When that transaction in that channel is done, then that transaction is endorsed and can show up in the order. So what Fabric 1.0 is going to ship with is a product called Apache Kafka, which is a fault-tolerant, but not Byzantine fault-tolerant, sort of ordering system. It's been used in enterprise essentially forever. It's not something that Fabric or the Hyperledger project invented for this purpose. It is simply reusing an existing fault-tolerant distributed system that is fairly battle-tested for the purposes of ordering Fabric transactions, but it is not Byzantine fault-tolerant. So you have this, that is the out-of-the-box order. It is failure-tolerant. So if a node that is, so you have so it's like, it's a distributed system inside a distributed system. So the distributed system is this ordering service. It has basically one identity, but that identity is made up of multiple instances of Apache Kafka. Apache Kafka is ordering the data. If one of those nodes goes down, everything remains consistent and it continues to accept transactions. So, and Apache Kafka, I think for many of the enterprise developers in the room, is a familiar technology. And so you have this Kafka order, it is failure tolerant, and based on its like sort of API surface area, it doesn't actually inspect any of the transactions. So that's the sort of out-of-the-box 1.0 architecture.
Are you drawing a fine distinction between failure tolerant and fault tolerant?
So there's a distinction between Byzantine fault tolerant and failure tolerant, or fault tolerant.
Okay, fault and failure tolerant.
Fault and failure, I'm saying, are basically kind of the same thing. The distinction is between Byzantine and non-Byzantine faults. Though if you say Byzantine fault tolerant and then fault tolerant, it's like hard to parse what it is that you just said. So I'm using the term failure to describe non-BFT systems. But basically, a BFT system would be like, oh, I hacked into your orderer, and now I control 40% of the nodes in your orderer, but I continue to order correctly. In Kafka, if you've hacked into the system, you've hacked into the system. All the malicious things that I talked about on the previous slide that a malicious orderer can do, once I've compromised your Kafka orderer, I can do all of those terrible things. Does that make sense?
I'm not sure. Is the difference that failure tolerant is just some nodes go down as opposed to Byzantine fault tolerant that someone is actively trying to give you the wrong answers?
Yes. So the difference between failure tolerant and Byzantine fault tolerant systems is failure tolerant or fault tolerant systems if the software crashes or the power goes out on one node. The system keeps chugging along.
That's failure tolerant.
That's failure tolerant, fault tolerant in the literature.
Yeah.
If you are Byzantine fault tolerant, you are actually tolerant to one of those nodes starting to try to trick or communicate to go all the way back.
Okay.
You have now built a system where you have a traitorous lieutenant and the system still works. And to be clear, Fabric 1.0 is shipping with sort of the most developed orderer is a failure tolerant or fault tolerant orderer, not a Byzantine fault tolerant orderer. So it really relies on this not being hacked or not being evil.
But the malicious things you can do if you successfully hack it are limited by the privacy and the encryption, right?
Yes.
So ultimately the system as a whole is still retains the Byzantine property, right?
Yes. And I like that the order of my slides communicates this. So I'm very happy with myself. Basically what happens is you have, so this is the bad stuff that an orderer can do, whether it's evil or compromised or just having a bad day. This is your mitigations. This is why you think you can get away without a BFT orderer. This is the non-BFT orderer. This is what Kafka is doing inside of Fabric. So now you get to, yes?
Can you walk us through the previous slide?
Yes. Okay. You have a Kafka cluster. So this is some arbitrary number of computers. It's like 4 to 8, let's say. They could be virtual machines, they could be mainframes, who knows. You have the ordering services nodes, which basically, because Kafka doesn't know anything about blockchains or Hyperledger or anything, it's just this piece of enterprise software that basically puts things in an order. So the ordering services nodes are reading the output of Kafka and of that Kafka cluster and being like, now I'm going to convert that back to speak Hyperledger. I'm going to pull things in, send them to the Kafka cluster can put them in order, and then these are just translation stuff. And then these are your actual Hyperledger peers, except there's in a more complicated diagram, there's infinitely many. Does that make sense?
Yeah.
Cool. Yes?
So if you hack into the Kafka cluster, the privacy is retained.
The privacy is retained.
Compromised, but so it seems like the system is relying just on the fact that the hacker won't have any motivation because he can't gain anything by hacking?
No, you can totally gain stuff. You can gain stuff by you can denial of service the network.
Yeah.
There's a variety of ways you can denial the service network. You can maybe do channel censorship, as Natalie was saying. You can do you can totally screw with anything that's in the system chaincode channel. In the unencrypted channel, you can do terrible things.
So isn't that an issue though? I mean,
it's totally an issue, and that's how we get to my next slide. So this comes down to why we make consensus pluggable. It might be, we don't know. because nobody has really run these things in production, and nobody has ever defended against it being hacked, and nobody has ever run high-value stuff on anything like this before. So maybe it's going to cost like a huge amount of money. I mean, IBM's talking $10,000 a month for a Kafka host, essentially, for Fabric. So maybe it's really expensive. Or maybe I have really important functionality in my open system Chaincode channel. Like that's the channel in which we send money to each other. Because if you want to have a globally consistent ledger of value rather than just a set of data channels that you can collectively compute with your counterparties with, you will need to do that in the open channel. And in both of those situations, maybe you might want to find yourself with another orderer that isn't as vulnerable or isn't as expensive. So, for most of the history of computing, there were not many choices in Byzantine fault-tolerant consensus. There was essentially one. It was called Paxos. It came from the same paper that I started out with. But now, hardly it seems like a day goes by without a new Byzantine fault-tolerant consensus algorithm. This is Algorand. I guess I forgot the screenshot of the paper. Honey Badger, Tendermint, BFT Smart. This is what Symbiont's assembly product uses. IC3 is trying to productize that. This thing raised $17 million like 2 weeks ago. Turing Award winner. But like it seems like, and my general point of view on this is I think we're going to not, I don't think we're like anywhere near like peak number of consensus algorithms. We're going to have so many. Mostly because I think that they're not actually like a unified thing, that there's actually discrete modular components of a consensus algorithm, and people are going to want to make different choices about how those things are assembled. But that's a computer science problem. Go ahead.
Is that like flexible in terms of the consensus mechanism?
Yes. In fact, you could theoretically, or like my gut estimate on like resources would be implementing taking the existing Tendermint code base and implementing as a Hyperledger orderer is like a week of work. Honey Badger, the crypto primitives are much more exotic, so more than a week of work. Some of these other things, like it took Symbiont maybe about 4 months to do their BFT Smart implementation. So I don't know whether you could, in theory, probably reuse theirs, but somebody would have to come up with an economic model that made sense. But these things exist. Now, the process of building Fabric 1.0 required building a lot of things. And the thing that they chose not to build is any of these things. I think they have good reasons, because IBM does have secure computing environments that they can use for running Kafka. A lot of the initial use cases that they're looking at are things that are primarily going to be done in the secure private channel. And so as a result, they didn't really invest a lot of time and energy here. But I think that this will change. What those algorithms buy you is this. They constrain the power of the orderer or the orderer. They give you some safety threshold. They say like until 60% of the ordering population of nodes is compromised, everything is fine. And so you get compromise resilience. Like you not only get the ability to add people that you don't necessarily believe are going to play by the rules and be fair, you also get resilience against the guy that you really trust and brought into the system and you know would never do anything unfair and never violate the rules. When he gets compromised, you don't have to worry about the system. So I do think BFT consensus is going to be valuable. And any blockchain project that you're doing, I think it is valuable to think, do you need BFT orderers, and do you need your Chaincode endorsement policy to be BFT, and what does it actually mean if your Chaincode endorsement policy is BFT? And we seem to be we're definitely in a very early stage of thinking about this stuff. I'd say the biggest thing going on right now is, and why we're trying to figure this out, is nobody has yet figured out what is the economic model to take any of these things and turn them into a consensus algorithm. Like, the only reason Tendermint exists is because Jaquan is the kind of person who, if you tell him to build a proof of stake cryptocurrency, will invent a new BFT algorithm for some reason, which is a good idea. Honey Badger is a set of excellent academic work, so is BFT Spark, so is Algorand. There's not really, we've not yet figured out in enterprise what a monetization model is for this layer of the system, which is why we end up with Kafka, which at least has a monetization model because you can charge $10,000 a month for it. I'm kind of winding down towards the end. I've been talking for a little while, and hopefully you can badger me with questions more. This might be more interesting. My sense of things is, of the applications I've looked at, for supply chain, healthcare, and regulatory compliance applications, I have not seen a compelling reason why you need a BFT order. I haven't really seen like a good argument of like, this terrible thing is what the orderer will do. In general, things happen slowly, etc. You can take your picture. You can also have the slides. These are applications that I think BFT needs to be considered. There are definitely privacy technologies that you can implement that are an alternative, but payment and value transfer, market making, I said market twice, there's always one misspelling in my slide decks, and any sort of trading. Auctions are another good example. Anytime you're running these kinds of systems in a blockchain environment, BFT applications, like the canonical use case for Cosmos and Tendermint is a decentralized cryptocurrency exchange. And if you are running a decentralized cryptocurrency exchange, you better hope that you have a BFT you have a BFT consensus algorithm, because you will not have any settlement finality if your safety thresholds are exceeded. So we're starting to get a sense of what the production requirements are for orderers in these kinds of systems. You need HSMs. So if you go back to this layer, you would want HSMs on these nodes so that the cryptographic signatures that says that this order is the order that happened are very difficult to forge. You want, so, yes?
Sorry, I don't understand HSM in this context.
Yes, hardware security module. It is a technology that contains a cryptographic key, and it should be very, very hard to get that cryptographic key out of that module. So typically, like, how does a Bitcoin exchange get hacked? A Bitcoin exchange gets hacked by, you hack into the systems, you find the cryptographic keys, you copy the cryptographic keys out of to another system. It's something we call key exfiltration, and then you go and you use those keys to sign transactions. HSMs, in theory, make this impossible, at least very difficult. Orderers are going to need to be extremely highly available. There's almost no, like, one of the glorious things about the way Bitcoin operates today is, the Bitcoin mine in that office park catches on fire, the whole thing burns down, the network keeps going. In this world, you are going to have, depending on what level of fault tolerance and failure tolerance you have chosen to set up your system with, you're going to be able to survive. You're going to continue to have an operating blockchain under some amount of failure, but not a tremendous amount of failure. If all of your orderers are in a single data center, and that data center has the power go out or burns to the ground, you don't have a functioning blockchain anymore. And then the next thing and the final thing you need is a significant amount of physical security. Because you can do the terrible things that are on the previous slides if you compromise the system, well, you need both digital security and physical security. These are probably going to be some of the most security-intensive systems that we have ever built if they are actually going to run high-value transactions off them. And so there is an incredible need for people to figure this out, and these are the kinds of things that startups are ill-equipped to do, but Oracle is here, and you guys have data centers with physical security, and you guys are good at building high availability systems. You are okay at digital security. But there's a lot of contribution, and these are the kinds of things in order to sort of bootstrap blockchains into big enterprises. It's very difficult to imagine how startups like SkuChain are going to do it all by ourselves. So this is my take.
I just have a question. I mean, one of the beauties about the blockchain, of course, is the decentralized element.
Yep.
What you just described is the order of the central point of failure.
Yes.
Right.
System.
Yes. Damn straight.
That's it.
Probably some amount of legal.
So my philosophy on it is decentralization has become like this weird, like almost religious statement about systems. My view of what the point of a blockchain is in the past, everybody, every enterprise, every corporation, every individual has had their own system of record, whether it was their personal accounting software, their business ERP, the system they call core or core 2 or new core or new core. And all of those systems would communicate with other companies' core systems, and they would have, but it was inevitable that there would be difficult to reconcile differences between those systems. What the point of Fabric is, from my point of view, is to create, for the first time, a computing environment in which there is a shared system of record between them. Now, if that shared system of record relies on a centralized orderer, other than the fact that this stuff is hard, I don't have a problem with it. I don't think it undermines the value proposition at all. All of the value proposition that SkuChain's business model extracts out of the blockchain is possible, and it is in fact fantastic under a regime of a centralized order.
So you're saying the resilience is compromised, not necessarily the underlying data.
Yeah. You still get this wonderful thing, this wonderful property of a blockchain, which is I can somewhat more easily take the network offline, but I can't come in and say, I can't corrupt the data. I can't change the data out of the rules of the system without essentially globally compromising the system.
Thank you.
And no matter how much I compromise the orderer, well, I can produce one of these alt chains. That's my thing. If I completely control your orderer, I can essentially, to a limited extent, because I can take all of the transactions that ever existed and recreate them into some new order that makes sense, in theory. It'd be really hard in practice, but in theory I could do.
How would you do that?
Huh?
How would you do that? Every peer has a copy of the ledger.
Yes.
And the ledger's got typical cryptographic hashes chained back. So how do you change the state of the peer that's already been recorded?
So what I do is I own these machines. Now that I've owned those machines, now I have a peer I've seen blocks 1 through 10,000. I compromise these machines. I make a new set of 1, 2 through 10,000. Those both sets are equally valid from a cryptographic point of view. Now, one I know I got from the network over the last 3 years, and the other one I just got today. Now, any rational, logical person and anyone who's doing forensics on the logs is going to go, yeah, no, like these machines got owned, and that's why this like new blockchain showed up. But in theory, I don't have as strong a set of guarantees that tell me, no, this new blockchain is fraudulent, and my old blockchain that I've been sitting on for all these years is the true one.
How do you rewrite blocks that have already been recorded in here?
Because, so Fabric today would actually not, would just like fail. If it was, because like, and it's an invariant in the system that you should never receive two different blocks at the same height. But in theory, there's no way of differentiating between two correctly signed blocks brought from your ordering service at the same height.
Even if you get them at the same height, you can create a fork, but I don't see how you can change the path.
You don't. You just create. You're right.
So it's a fork. It's not an alternative blockchain.
Yeah, it's not. It's an alt history.
But you could go back anyway. If you didn't have two forks, you could go back
To the beginning.
No, you can't. You can't. There's nothing in the Fabric protocol that would allow you to do that.
I agree. It would fail.
So, this is sort of peripheral to your main talk. That, you said something about production blockchain is not existing, right?
Yeah.
Now, the advertisement is that there's this Northern Trust application that's running in Guernsey, right?
Yes.
So do you know what they're using? And it's sort
Yeah,
of
mainframes, HSMs.
Right. Now, how do you contrast the HSMs with the SDX enclave?
Oh, that's a very politically sensitive conversation that you just wanted to have. In theory, Intel has. Yeah, I'll repeat the question. The question is, how do you contrast the HSMs that are sitting in the IBM mainframe with SGX? In theory, Intel has put something very much like an HSM, and far easier to program, though not exactly easy to program, into every new computer via this thing they call SGX, which is this little secure computing enclave. And it would be super great if anybody knows anyone who can convince Intel to start shipping enclaves for Fabric HSMs inside SGX enclaves, and it would make everybody's lives super easy. But to the extent to everybody I know in the cryptographic community who has tried to convince Intel to do this, no one has succeeded so far. So that is the political sensitivity of it. Like, I would really love to live in a world where I could where SGX on Intel Xeon existed, was available, and we could run SGX enclaves as the HSMs for all of these things. It'd be like super great. Doesn't exist. IBM's HSMs and Gemalto's and Thalys's HSMs exist.
So your assertion is that practical SDX enclaves don't exist.
From the point of view of a working cryptographer, as a practical matter, SGX kind of doesn't exist, except for writing attack papers. But I really wish that was not true, because it would be really, really great for us, for like blockchain deployments. Like, it would be so great. It would be such a massive accelerator. So if anyone knows anyone high up at Intel and can convince them of this, that would be great.
Is SGX as secure as HSM though?
That is a very complicated question. It can be. Yes.
I got in and out of the talk. I followed mostly, so you might have already
Yeah, go.
address it. What about the tokens? How do they work? Is there tokens like on Fabric?
So Fabric really doesn't have any support for tokens right now. So the natural thing to do, and why this is a really complicated question, because I think I have sort of a slide on this. Yeah. So Fabric is going to ship without a BFT orderer. If you have tokens, the natural place to put tokens is in the system chaincode channel. If you have tokens in the system chaincode channel, and you really want some privacy technology, like confidential transactions or something like that, and then you really want a BFT orderer, so the orderer can't, delay your payment. And so this is like this interesting dilemma that has been constructed around, because IBM in their conception of the use cases for Fabric, and if you look at these use cases, and if you look at what IBM's actual announced POCs are, it's all in this category. It's not in this category. So if you're doing pilots, POCs, production in this area, you aren't gonna build a system for tokens. It's the people who are building systems in this area that build systems for tokens, which is why they're designed so differently. And somehow, over the next period of time, because we are seeing a world in which you might have, where stuff that happens in this world might eventually turn into stuff that you might want to have tokens for, we need to cross this barrier. And part of it is solving the orderer problem, but there's a lot of other technology we have to build. Yes?
Might be a naive question, but why would you need tokens on a permissioned chain?
Because, let's say I have a bond and I want to give it to you because you bought it. That's like a token. Like any sort of asset that, so there's a utility, so that, it's actually a little bit, so this is a complex question, but there's a utility value to tokenization of assets. Like, why are cryptocurrencies worth anything at all? Unclear why. It's really cool that they are, and it's fascinating, but it's unclear why. But clearly part of it is the utility value. Part of it is that you have this asset that is so easy to move from one party's control to another party's control that you can write programs that manage. Like, clearly utility value is part of the story. And if you have tokens on a permissioned ledger, you capture some of that utility value. And so there's a natural inclination towards doing tokenization on permissioned ledgers. Though it only became obvious to me that this was true like a few months ago.
So just for clarification, how are you defining a token, or what are the properties of this?
Oh, that's a good question. I have never expressed this. So we'll see. The question is, how do I define a token? The token is a unit of value that can be transferred from party A to party B, and essentially functions as a bearer asset. So party B can then go and either liquidate that token into another system, exchange that token for dollars, go to an exchange of some kind or a bank, get fiat currency for it.
So it's cryptographically sort of independent of the original asset, or linked?
It's cryptographically linked, but it becomes an effective proxy for the underlying asset. So it is a bearer proxy for an underlying asset, is actually my definition of a crypto token. But I haven't really explained it before, so good question, thank you. Yes?
One of the consensus protocols that seems to be kicking around, BFT Raft, wasn't
Yeah, I'm not a fan of BFT Raft because I kind of don't believe it exists. Yeah, I wish I had time to like academically defend this point of view, but my actual thought process on it is, so what Raft is essentially is Raft is a system by which we can, so in a functioning Raft system, I could do a Raft talk later at some point, but in a functioning Raft system, the leader is elected once. And from the point of view of, so from the point of view of once you've elected a leader, that leader is functionally identical to that Kafka cluster. Like that leader is the order for the network. Now if that leader goes down, you can rerun the leader election, and what BFT hardened Raft is basically trying to defend against the situation where I'm a malicious observer, I've compromised a peer, I take the leader offline, and then I manipulate the election process to ensure that I become the next leader. And BFT hardened Raft is basically against that threat model. But in a proper BFT system, like any of these systems, the leader can't even do any of these things with some constraints.
So in a Raft, you're saying the leader can?
Yeah. It's really,
on its own.
Yeah, the leader can do all of these things on its own. And if you actually solve all these problems, you pretty much end up with Tendermint. Like essentially the sort of abstract design problem of Tendermint is like start with Raft and then fix all these problems, you end up with Tendermint. Yes?
Can you explain, maybe it's too obvious to others, but can you explain why supply chain and healthcare and those other things can work with a non-BFT?
I was wondering the same thing, especially for healthcare.
Okay, good question. Yes, and I did not defend this at all. I just said it. The question is, why do these applications not require BFT? The reason these applications, in my mind, do not strictly require BFT is, like, let's say I decide to censor an invoice, okay? I've censored the invoice. Like, these things are really friendly towards private channels. So you're going to have what the application architecture that I imagine will be dominant is that for a given supply chain you will have a network with an orderer, and then you have many bilateral and multilateral channels. But the orderer will be extremely dispassionate towards the behavior of any of those channels. And then what you will see, and so if the orderer wants to like mess with a specific channel, like what's the worst thing it can do is it's not going to like make the goods disappear from your ship or like cease to exist. It can cause some chaos and confusion, but